come back in. I can come back
Yeah.
and start again.
So I will disappear myself. So once you finish, you can just leave this thing. If it doesn't stop by itself, I will stop it at some point. Yeah.
Okay, cool.
So yeah, so everyone enjoy the session, and you can see the chat. Let's see. Let me say hello just in case.
You don't have to do this just for me, because like I said, I'm not sure I can even stay, and I haven't watched the whole lecture yet. Unless you want to do the recording.
It's okay.
That's
The
what we are
recording
doing,
of it is. Yeah.
Yeah, we are doing recording for the others who cannot attend, maybe because of the time zone conflict. Okay, someone else is joining, Stefano. So maybe,
Oh, good.
Stefano, I hope I accepted you. Yeah. So Stefano has joined. I actually need to hang out because this is an enterprise thing. I need to hang out for a bit more to let people join.
Can we make it open at all, or?
It's just the configuration in our company for our
thing.
Okay,
sure.
Yeah, so it's not a problem. I can hang out. Yeah, to see if more people join.
I appreciate it.
Yeah. It's okay. It's okay. Don't worry. Yeah. Let's see. I don't think any more people will join. Let's see. Is our other friend Antonio Jesus? He was on the other thing. I hope he got the message. We go back to Crowdcast. Yeah, let's give it just 2 minutes, Brian, please, and then.
Yeah, of course.
To make.
Yeah, these things will be helpful for some of the concepts I'm going to talk about tomorrow. Just some of these.
Yeah. Okay.
They're like baby cases of universal properties.
Okay. Okay, maybe I need to tag everyone to send a notification to say at everyone. Yeah, at everyone. We are live on Google.
Whoops.
On Google above. Yeah. All right. Yeah, people will see the message also when they join the Crowdcast with the link and everything. Yeah. So I will just so everyone, Stefano and Dimitri and anyone else who join, you can just feel free to ask any questions on the chat, or just unmute yourself and ask.
Yeah.
Unmuting
yourself will be the easiest, so I can just know to check, because it doesn't push notification to me when I am in the other screen.
Yeah, so maybe it's better to just speak and
and then I'll check every problem or so.
Yeah, no worries. Okay, yeah, so I will disappear, put myself invisible, and mute myself. So yeah, Brian, the floor is yours. Thank you so much for doing this.
Of course.
Yeah, I hope you guys, everyone else, enjoy.
I hope you, any of you who have stuck around long enough to be at this point in the problem session, thank you. Some technical difficulties in the beginning there. So in the video we had for lecture 1, there were only a few exercises. I think I had maybe 5 that I planned. And I added a 6th one, man. I might just post in the Discord channel or go over later on today. So the first exercise was about the category of sets, and in particular about the empty set. So, this over here. So it was in this case right here. So the way we characterize the empty set was it satisfies this following property, that for any set X, the empty set is a subset of X. This is the classic definition of the empty set. And so the way we framed it categorically was in terms of morphisms. So for any set X, there's a unique morphism from the empty set into X. And you can phrase this in terms of homosets like this. So the morphism from the empty set into X is a single morphism. So the first exercise is showing that this actually uniquely defines the empty set. It's the only set that has this property. So remember how we proved that two sets are equal. So if I claim, for example, that there's another set A with the same property. So suppose A has the same property as the empty set. So A is a set. So namely, that for every set X, every X in the set, there is a morphism, it is a unique morphism from A to X. So I claim that not only is A isomorphic to the empty set, it's actually equal to the empty set. So the way we prove that is the following. So remember, two sets are equal. So A is equal to another set B if A is a subset of B and B is a subset of A. If and only if. You can do if squared, or most people write IFF. Right. So we already know by assumption the empty set is a subset of A, right? Because it's a subset of every set. This is its defining property. But, well, if A has the same property as the empty set, then by assumption we have this. But also, we know that there exists a unique morphism from A into the empty set. So A from A to the empty set is not empty. And so in particular, since the empty set has no elements, this can be recognized as A is a subset of this. I can take these following two things, as D set goes to A, call that I1, and this as I2. This is equal to just morphism I2. And so these two things, so you want to think about it as this, but you don't necessarily know it's a subset. You have to do a little bit of work to make sure you understand those two things work. So the only way this can happen is if A is actually equal to the empty set. It's just a very similar property to showing that identity elements are unique in groups. Right? So how do you show that? That's something like if I have an identity element E1 and E2 in some group G, you know that they're actually the same element because E1 is equal to E1 times E2. But by the property of the identity, they both satisfy this equality. This is very similar. And in fact, I called this thing an initial object in the category of sets. So an initial object is something that satisfies. So let's say X is an initial object in a category C if for any element, say Y of C, there exists a unique morphism from X to Y. And you can show using the same exact argument as above that this defines X uniquely up to isomorphism. This property uniquely defines X. Up to isomorphism. Cool. This is always true using the exact same argument. Okay. So for exercise 2, I wanted to formulate the same kind of analogous property for the terminal object, which is the singleton set. We showed that, any two singleton sets in the category of sets are in bijection. They're isomorphic sets. So it's the same property. You'd say, I'll call it Z is terminal in the category C if for every other element or object you have a unique morphism from Y to Z. It's sort of the same property as initial object, only the direction of the arrow is reversed. And I think I defined the opposite category at some point, right? Somewhere over here, maybe. Yeah, right here. So in terms of this definition of something called the opposite category, the category. So it's the same set of objects, but you reverse all the morphisms. You use this idea of terminal and initial objects to say the following, that, or to spell out. Okay. So for example, X is an initial object. In C, if and only if squared. If and only if X is a terminal object in the opposite category, C op. So maybe this is something you can treat as a little exercise, that the property of being an initial object is the exact same thing as being a terminal object in the opposite category. So there's two different ways to look at the same property. And we kind of take time to focus on these, two definitions, because the next topic we're going to talk about tomorrow, in terms of universal properties, every universal property to be thought of as an initial object or a terminal object in some suitable category. It's a very powerful framework. Just check to see if there's any messages. Dualization. Well, it depends on how we frame duality. So that's one of the questions: is this somehow related to dualization? It would depend on how we phrase duality. So the duality here, for example, is between a category and its opposite category, but also any kind of sufficiently good structure of a problem or analogy is some universal property somewhere, or some function lurking around somewhere. So I wouldn't be surprised if once we formulate it in the right way, it's something of this form. So let's go back. So this is, we just did exercise 2. So exercise 1 and 2, we first were motivated by the category of sets, which is usually your first kind of intuitive introduction to categories. But now for the category of vector spaces over a field, say K, what is there an initial object or a terminal object? Yes. So the answer is yes, but we can be a little careful here, because unlike the category of sets, we notice that the empty set is not a vector space. right? Because a vector space always satisfies something specific. It has to have a 0 element. So any vector space, a capital V, contains a 0 element. Say, 0 is an element of V. And in particular, if we're very sneaky, we could think about it as the inclusion of 0 into a vector space is always a linear map. Is linear. Yeah, linear with respect to K. Likewise, so, or maybe on the other hand, vector spaces are, sets with extra structure. And we know that every set has unique morphism to a singleton set. So in order to make that linear, we can just say any such vector space V admits a unique morphism to the 0 vector space. That exists a unique map to the 0 vector space, which just sends every vector, say, V to 0. And so we actually find that in the category of vector spaces, there is an initial and terminal object, and they're the same. The 0 vector space is both initial and terminal. Oops, my handwriting is terrible here. Initial and terminal. And in fact, when you have such a category with this property, you would call this thing the 0 object. There's something similar in the category of groups. You notice, like in group, the group containing only the identity element is a 0 object. Cool. All right, so I'll come back to this one here in a bit. So I mentioned that something called the power set, which we thought of as it is partially ordered set ordered by inclusion. It's a complete Boolean algebra. It's a post set. We can turn this into a category ordered by inclusion. And it turns out, I'll just do it now, I guess. You can represent this in terms of morphisms. So this is the power set right here. The power set of X. I claim it's the same thing as the set of all morphisms from X into the 2 element set 0, 1. And this is because I can do the following assignment. So for any subset A of X, I can assign the following function. So I'll map that subset into the function from X goes to 0, 1. I'll call this chi sub A. It sends a little element X into 1 if X is in A, and 0 if X is not in A. Sometimes call these things a characteristic function. Function of A, of the subset A. And you can imagine this, any such function from X going into 0, 1 defines a subset. Likewise, so this ends up being a bijection. which in the category of sets is an isomorphism. You can do this more generally for certain categories. So in the category of sets, 0, 1 is called a sub-object classifier. Right. So how do you think about post-its as some kind of topological spaces? Well, only certain kind of post-its can be thought of it that way. The example I was referring to before was over here. So for any topological space, I can consider its collection of open subsets. So this is a set. Its elements are open subsets of X, and they're ordered by inclusion. So you can look at, you've got some topological space. So this is X, and some open subsets here. So maybe this is like U, this is V. So these things are not comparable, but they both kind of include into X itself. If I had, say, W here, then I have like U intersect W is a subset here. So you can always realize any topological space as a category in the way by looking at its collection of open subsets and order them by inclusion. And for certain kinds of nice post sets, you can vice versa think about it as sort of defining a topology. The way you do that rigorously is with something called, you should look up, is they call it a Grothendieck topology on a category. This is the way to make this precise. You can think about these things as elements of your post set, to think about them as like open sets and collections of elements of the post set as sort of like open covers in a nice way. So this is something you might be able to find in the references. So quick this up. Sorry. Man, I dropped the ball by not bringing a full-on computer and only using a tablet. Yeah, it is a really beautiful idea. This idea is explored in the book, in the reference, say by McLean, and I think it's more, I don't know how to say the name. And so the reference list is posted in the Discord channel, and it's also posted on the GitHub repository for this class. So in this way, you can realize certain kinds of nice categories as something that comes from geometry and also something that comes from logic. They end up being the same type of thing. This is kind of unified. The notion of a topos, which is like a super nice kind of category. In fact, topos was supposed to originally be, this like generalized idea of a space, a universe in which you can do mathematics. Grothendieck really kind of saw further than a lot of people in this way. Right. So to do this, sorry, let me orient that thing right. This more exercise right here, exercise 4, the statement that a group is the same thing as a category with one element where every morphism is an isomorphism. We want to first start with the previous example where I talk about monoids. So recall a monoid is a set with a binary operation. So it's basically like a group, but you don't necessarily have inverse elements. So the examples we kind of talked about were, you say the group of integers under addition versus the monoid of natural numbers under addition. Since you don't have negative numbers, you can't really always undo addition. So we can think about a monoid as a category with one element. So you have, say, one element, maybe the symbol M. Do M with a circle around it. So you think about this as like a one element set. This is just like the symbol M. And the elements of this category, so there's only one thing, and then the morphisms from M to itself are exactly the set of elements of the monoid. So you just think about, so like X is an element of M means that X going from M to itself is a morphism. Yeah, concrete example. So we'll work with the example of M being the natural numbers under addition. So I'm not a heretic, so I think that I always consider 0 to be an element of the natural numbers. Some people say it starts at 1. I think that they're wrong, and they should just not speak. I don't know. I don't really feel like strongly about it. Or you can think about this as just like, z greater than or equal to 0, whatever. So in this case, I'll think about, the set n. So each natural number can be thought of as a function from n to n. You could think about this as maybe like if I take a natural number little n and I add m to it, I'll call this morphism m. So this is it belongs to the set of morphisms from n to n in this category. And I'll call this category n with a line under it. And so in this case, function composition, let's say I do, if I have two natural numbers, k and m, they define two morphisms, addition by k and addition by m. So if I write like k of m, it's sort of like n goes to m, or n plus m. I can't decide on how to write my little k's, which goes to n plus m plus k. And addition is associative, so we know function composition in this thing is associative. Thanks. 0 in n team. So in this case, so unfortunately, these morphisms are not all isomorphisms, right? These aren't surjective. If I do the example, the morphism 2, where an n goes to n plus 2, like 1 and 0 are not in the image of this. And so this morphism isn't surjective, so it can't be an isomorphism of sets. So what we say in this case, a group is exactly something where that is fixed. So if I did the same exact kind of argument now, but I did like my group of integers under addition, if I did addition by 2, right? So like n goes to n plus 2. This is suddenly an isomorphism. This is surjective and injective. And injective. And this is because every element in a group has an inverse operation. you can, so in general, you can think about a group. I have some element in the group, say little g. I could think about the function, which is going from g to g, to multiplication by g. So I can say h to say h times g with the group operation. This has an inverse g inverse, right? By the axioms of a group. Inverse of h to h times g inverse. So as functions, g and g inverse are inverses. And so they actually are isomorphic, or isomorphisms in the categorical sense, which I defined up here somewhere. I don't know where I defined that. Somewhere in the set of notes. You can also, so you mentioned rings. Rings themselves aren't a nice category, but if you want an example of a ring, the classic example is just the set of integers with addition and multiplication. So it's an abelian group under addition, and it's a monoid under multiplication. You can't always multiply it by the inverse of an integer. So like 1 and -1 have multiplicative inverses, but like the multiplicative inverse of 2 is not an integer, which it's 1/2. So this is a ring. If I want to do like Q, the rational numbers with addition and multiplication, this is a field. So, we saw that you can turn a group or a monoid into a category in a nice way. You can't really do the same thing with a ring. It's not really as well behaved. And the category of rings themselves isn't really like a nice category. You can define it. You have to be a little bit careful about what you mean by ring morphism. Like to use then like one to itself. So you only have the category of commutative rings. So there's a little bit of work to do there. But you have like the category of vector spaces over a field. So the vector spaces over Q is nice as a category. Likewise, the category of modules over a ring R is really nice. The category of rings is not. But if you can make it into a category, but nobody does. Only the cool people ignore that. So let's go a little bit further. So the last exercise was about this operation for vector spaces called the dual of a vector space and the double dual. So this is something that maybe the only exercise that's like you might say is hard. The other ones are kind of just take a little bit of time to get into the mindset, and then once you get into the mindset, it's not too hard. So what I want to do is define a function. So for any vector space, V, in the category of vector spaces over a field, K, I'm going to define a function. It goes from V into V double dual. So, did I write that notation anywhere? Yes, which is the dual of the dual. I'll call that delta V. So let's define this thing. So what is V double dual first? So V dual is the set of linear functionals on V. So the set of functions from V into the ground field K. If you guys are have done a little bit more linear algebra or maybe some like vector calculus, this might be a distinction between vectors and covectors or tensors. In quantum mechanics, this is like your Bra and Ket notation. So in this case, V double dual is the set of linear functionals on V dual. So it's a set of functions on the set of functions. Or in other words, it takes a function and produces a number. All right, so what I'm going to do is I'm going to take an element of V. We'll call it little V hat, like a little arrow over it. And I'm going to send it to the following functional. So what I'm going to do is take a functional. This is inside V star. And I'm going to send this, sorry, this is getting a little meta here. I'm going to send it to the functional evaluate at V hat. Right, this is in K. So the way you should think about it is equal to the functional evaluate on V, on the vector V. Evaluate the functional at V. It's a little strange to write down, but when you follow your nose through it, it ends up making perfect sense. You take a function from V into K, in V, and then you evaluate it at this little vector. And that process of evaluation is itself a functional. So it seems a little awkward, but this actually defines a function here. So we have, for all choices of vector spaces, big V, we have this function from V into the double dual. And so when we are a little bit more careful about this, what this actually defines is a function between functors. So the identity functor on the category of vector spaces, okay, into the double dual functor, which I'll call delta. So this is, delta is a function between functors. Whatever that means. That seems kind of weird to write down. The specific notation for this, the name is, it's a natural transformation. We call this a natural transformation. When you restrict to the category or the subcategory of finite dimensional vector spaces, this ends up being actually an isomorphism for every V. And so you'd say, restricted to the subcategory, I don't know, I did it a bit, like the finite dimensional vector spaces over K. Delta is an isomorphism of functors. It's a natural isomorphism. But the problem is when you have an infinite dimensional vector space, this is just a natural morphism. It actually ends up being not an isomorphism in general. And maybe it's a good example to come up with a case where we have an infinite dimensional vector space, and this is not an isomorphism. So I'll leave that to you guys. So, why? How you guys figure that out? Okay, so that's really all the exercises I had planned for you guys. Going back to end my screen sharing. Stop sharing. Put my screen back. Cool. So next time I'll make this a little bit, more seamless where we won't have to spend 20 minutes on tech issues. But thanks for showing up. Let me know if you guys have any more questions. If you can post them in the Discord chat, it'd be great. Lecture 2 will come out tomorrow. And that'll be asynchronous, but I'll see you guys again.